So here's an example to show how this all ties together. This is an example that uses a real transistor, the NXP BFU 725F/N1. That's a silicon germanium NPN bipolar transistor. In this case, we're going to use it at 3.8 gigahertz. So we want to do a narrowband design. That is a design that is optimized for one frequency only at 3.8 gigahertz. And the task here is to do two things: minimize the noise figure and maximize the gain consistent with the noise figure requirement. So this is a very common way to specify a design. You say, I need the noise figure to be as low as possible, and then give me the maximum gain consistent with that lowest possible noise figure. We'll specify the input impedance to be 50 ohms, the output impedance to be 50 ohms. Here are the S parameters of that transistor in common emitter configuration for a set of bias conditions, which I'm not showing here. I'm simply showing the S parameters. The reference impedance is 50 ohms. And then from the same data sheet, I can pull out these three parameters. The minimum noise figure, which is 0.73 dB. What that tells me is that there is no way I can get a noise figure less than 0.73 dB out of this transistor. That's the best I can do. That optimum noise figure is achieved when the source reflection coefficient is this. So that tells me the source impedance, Z sub S, that optimizes noise figure. And then the noise resistance, R sub N, is given as 4.85 ohms. In order to use the equation I showed you previously, I must calculate the normalized load resistance. It's simply this divided by Z naught, and that gives me 0.097. So now I'm ready to do the design. First, check stability. Here's the factor delta. I find it's 0.365 at an angle of minus 91.4 degrees. The Rowlett stability metric K is given in the usual way by this expression. I get 0.732, and we see that there's trouble, right? It's only conditionally stable because the metric K is less than 1. So I'm going to have to proceed with caution here. We also know that there's no point in computing a maximum available gain because that concept only applies when we have unconditional stability. In this case, I would normally go ahead and calculate the maximum stable gain, but it's really not relevant in this case since we're asked only to maximize the gain. There's no minimum gain requirement, so there's really no need to calculate an MSG here. It doesn't really matter. We're not really trading off transistors or doing something where we're interested in knowing the MSG. We simply want to maximize gain subject to a constraint, so MSG just doesn't matter here. Now we're going to have to check whatever solution we come up with for stability when done. This is the consequence of being conditionally stable. So I can go ahead and run through the algorithm implied by my previous discussion, but when the smoke clears, it had better be stable. So first, select the source impedance. That's simple. All I have to do is set gamma sub S to be the optimum source reflection coefficient, gamma sub op, and that was specified. From this, I can calculate Z sub S in the usual way. I get 53.5 plus J 22.4 ohms. I know what the noise figure is going to be at that point, 0.73 dB. That was simple. Now I need to select the load impedance. The source impedance has been set. The load impedance is unconstrained at this point. Obviously, I'm going to use it to maximize gain. I maximize gain, and by that I mean specifically TPG, transducer power gain, by conjugate matching the output embedded reflection coefficient. No surprise there. So the load reflection coefficient should be the conjugate of gamma sub out. Gamma sub out, the embedded output reflection coefficient, is this thing. So I simply calculate that and conjugate it, and here is the load reflection coefficient. So this should be the load reflection coefficient, which maximizes now the TPG of this amplifier given the source reflection coefficient that I've already chosen. I compute the load impedance. I get 34.4 plus J 21.1 ohms. I compute the transducer power gain using the exact expression. and I get 18.5 dB. Now, I need to check whether that's a stable solution. I have a gamma S, a gamma L. Is this stable? Well, gamma out is 0.302. Gamma in, again calculated in the normal way, is 0.685 at an angle of minus 156.7 degrees. And these are both having magnitude less than 1, so the solution is stable. And stable by a comfortable margin, I'll point out. I only need for these to be less than 1, and I would like for these to be less than 1 by enough so that things like component tolerances and other uncertainties don't cause me to go over 1 in the actual implementation. These reflection coefficients are quite far below 1, so this is a comfortably stable solution. So this design is an example of a design where I've used a conditionally stable transistor to achieve a design which is safely stable. Here's the solution implemented using single stub microstrip transmission lines. I'm simply showing you the lengths of the transmission lines in wavelengths and determinations, whether they're short-circuited or open-circuited. I'm showing you the DC blocking caps. Here's a DC blocking cap here, DC blocking cap here. The positions of those blocking caps should now be clear to you why they are where they are, right? For example, this one needs to be here because I have a short circuit here. And there are other ways I could fiddle things around here, but this is just a starting point. And I'm not yet showing the bias. That would be another consideration. But the process of bias integration, of course, would be something that would be a substantial part of this design effort ultimately. In any event, this is a solution to this particular problem in which I have minimized the noise figure, it is 0.73 dB, and maximized the gain subject to that constraint. Now, I'd like to make just a few more additional comments on this solution before I move on. First is that even though this blocking cap isolates the bias from the short circuit, this circuit will have a DC input impedance of 0. In other words, looking in this way, I see a short circuit because the stub is short circuited. So if I have a problem with that, if there is some issue with whatever is to the left here, seeing a short circuit at DC, then I'm going to have to put another blocking cap here or do something to protect that device at the input from the short circuit. So just keep that in mind. That may be a problem in the actual implementation. Also note that resistors generate noise. So this is another incentive to strongly isolate the bias. What do I mean by that? Well, if I design the bias here and it has a bunch of resistors here and maybe here if I'm doing emitter degeneration, those resistors have noise. And the noise that those resistors contribute may or may not be significant. But this is an incentive then to do something clever. For example, if you're using a resistor here, you may be required to put an inductor here. Well, if you have a sufficiently high frequency design, I'll point out this is 3.8 gigahertz, that inductor may be a huge problem. Right? So this is where a lot of the pain and effort in design goes, is trying to figure out how to combine now the bias with the RF. I'll just point out here that this would also be a good application for this idea of the quarter wave stub impedance inverter. So for example, a quarter wave stub, I have the power supply up here and I connect to the point on the transistor that I'm trying to apply the bias to down here. Remember, power supplies typically have low impedance inputs, so this would have a high impedance input. This would be a way of increasing the isolation between the RF and DC in this particular design. So it is fairly common to see in very high frequency LNA designs and amplifier designs generally to see structures like this that are being used to provide RF and DC isolation. And the reason is because this structure does not require an inductance and it does not require a resistance to isolate those two things.